Hello everyone, and welcome to Live from the Lab. This is the show where we talk about different technologies that Bruker has developed to help scientists discover the world around us. Today's topic is in the world of single crystal diffraction. Now, typically we've talked about powder diffraction on this show, and in powder diffraction we think about our samples like sand on a beach, where it's made of an infinite number of tiny crystals in an infinite arrangement, kind of pointing in all different directions and completely random. In single crystal diffraction, we want to distill that down to a single grain of that sand, just a single crystal of it, and then investigate the structure of the atomic arrangement that makes it up. Now, specifically, what we're going to talk about today is something called twinning. And this is a type of a defect or a morphology in the crystal, which can cause some challenges when we're doing this analysis. So to learn more about this, we're going to head on over to the table and talk with one of our experts. Good morning, Michael.
Good morning, John.
So today we are welcoming Michael Roof, and he is one of our experts in single crystal diffraction. I would probably say one of the experts in the world of single diffraction.
Too kind, John.
Yes. So you've actually brought a few single crystals, huh, here. These are just very large single crystal pieces.
Well, it's not really a single crystal. It's just models.
Now, these are specific models, right? Because we talked about atomic arrangements.
Yep. So this is a model of a diamond,
okay.
And we'll talk about this a little later. And this is another polymorph of carbon. This is graphite, and we'll use these maybe later to describe symmetry.
And yeah, and as we all know, structure is very important because the properties of a diamond versus graphite, very, very different. So now specifically, though, today we're going to talk about something called twinning in a crystal. So what is a twin?
So you had described like multiple grains of sand on a beach. And indeed, in single crystal, we look at one of these grains.
Yeah.
But if you have a twin, that is a crystal that is comprised of more than one part or more than one domain. So it's two or more domains. And those domains, they're related to each other in a symmetrical fashion.
Okay.
So the symmetry can be if we have a contact twin, so two single crystals touching, and then it's the plane where they touch, which is called the composition plane. These parts might be related by mirror plane.
Okay.
Then you have crystals where they are related by rotation. Those are typically penetration twins. And then it can also be a simple inversion at the center of the crystal.
Okay, so this isn't necessarily like in the materials world where we talk about how a sample has many grains and they're very distinct crystal regions. These are actually going to be intimately connected at the atomic scale.
Mm-hmm.
Okay.
So it's important to understand that the twins share some lattice planes. Mm-hmm. And it's important that additional symmetry where these two parts are connected is not part of the symmetry of the crystal itself, of the intrinsic symmetry. For example, if you look at diamond, when you look at this model, you can see that you have, I'm too high, that you have a threefold axis here. So you can rotate this by 120 degrees, and you basically get the same image again. In a contact twin, for example, we could have a plane here, and then the other twin would be the mirror image.
Okay.
So for diamond, because this additional mirror plane is part of the symmetry, we wouldn't really have a twin.
Yeah.
At least not. Yeah. We would have a macroscopic twin, but maybe not in the diffraction pattern.
Okay.
But, a very prominent or very common twin, the spinel type twin, which is also cubic, but the symmetry is lower, and this is why this additional mirror plane is not part of the symmetry of the crystal itself. So then you get twinning.
So how does having a twin affect the diffraction experiment?
So if you have very high symmetry, then very often when you look at the X-ray experiment, and the X-ray experiment is just the Fourier transform of the electron density of the structure itself, what happens is that the symmetry is then maintained in the diffraction pattern.
Okay.
So you will get this additional symmetry introduced by twinning. You will also have that in the diffraction pattern. If you have high symmetry, then very often the spots are overlapped, completely overlapped. So determining the unit cell, so the smallest unit that repeats itself over and over, will be simple. But because you have an overlap of the reflections, then the intensity of the reflections that we need to determine the structure, this will be not right anymore.
Okay. Now, what would the traditional solution for this problem be? Just grow better sample, make better sample?
So, yeah, 20 years ago or so, or 25 years ago, what you would do is you would make this motion, and you would basically flip the crystal off the sample holder.
Just get rid of it. Sorry,
But
we're done.
nowadays, software has gotten a lot better.
Okay.
And especially with the introduction of the area detectors, it's also a lot easier to see from the diffraction pattern that you have twinning.
Okay. Okay. So it's really enabled then researchers to see all new materials, which in the past may have been too difficult to grow or just not possible to grow without twinning.
So sometimes, of course, and it's typically the more important your sample is, the more difficult it is, and then you have twinning.
Yep.
And nowadays you can still solve and refine your structure if you have a twinned crystal, which might not have been possible before.
So now I believe you've put together a few slides so we can kind of graphically see what this twinning is about.
Yeah. So what I will do is I will show you a little primer that just introduces twinning in real space, so what we can see, and also then in reciprocal space. So the nice thing about minerals is that they're stable.
Yes.
And they're typically larger than what we look at, you know, at Bruker, or what researchers look at. So you can actually see the twin, and there's some really nice twins. What I have here in this simulation, on the right side, you see a spinel twin. And let's hope this starts. So this sort of trigonal tabular prism, that's the twin. You can also see that it's joined in the middle, and it has concave faces, which do not happen in single crystals. And this actually starts out from a octahedron, and the twinning occurs on a composition plane that's parallel to the faces of the octahedron.
So now when you say composition plane, what is a composition plane?
That's the plane where the two parts touch.
Okay.
So what I did is I cut into that octahedron, and what I will do now is, because later I will have to mirror this polyhedron, I put it in the vertical direction. I will generate the second part by just duplicating the crystal, and then color it differently so that it's easier to see. And then what we will have to do is we'll have to mirror it. So what you see now is basically we have the composition planes on the outside. And when we mirror the darker blue one, now both composition planes where they will join are in the middle. If I put this together.
Okay.
This is basically how a twin looks like. That's not how they form, of course, because they will grow starting at that composition plane.
Yes.
And then often you see the direction is hindered, the growth direction along this 1-1-1 direction. That's the face of the crystal. And this is how a spinel twin will look like. I have one other example, and this is maybe my favorite twin. You can look these up. It's pyrite.
Okay.
And it's called the iron cross. So pyrite often crystallizes in this blue shape. It's a pyritohydron. It's a subclass of a dodecahedron. It has these irregular pentagons as faces. And in this case, the twin is a rotation around 001 which is a plane that goes through one of these edges here. And so I created a second part, a second domain. I will put them on top of each other. And now what I will do is I will rotate the second part by 90 degrees. And then you see how they interpenetrate each other. And when I get this exactly at 90 degrees, you see we will get that shape of this iron cross. But when you search for that, you will see pictures of these really beautiful pyrite crystals. It's very pretty.
Now, do these form to minimize the amount of energy in the system, or?
It's interesting, and I think that's still discussed. You could argue we have additional symmetry, so it should have lower energy, but that's typically not the case.
Okay.
In case of these contact twins, there's actually energy involved on the plane, and it's typically described as energy per area.
Yep.
Often what you see is there's a kinetic reason why they might form.
Okay.
But thermodynamically, the twin always has higher energy than the crystal itself.
All right.
So this was real space. So
Yes.
what we can see, now we look at some diffraction patterns. So here's an example of a cubic diffraction pattern. And it's only one plane, so two-dimensional to keep
Yes.
it simple. What we will do is we will have a threefold rotation around the center here. And when you look at the different colors, you will see that if we do a 120-degree rotation and then superimpose the images, nothing really happens.
Right.
So if the symmetry operation is a symmetry operation of the system, it's not a twin.
Okay.
But in case of the spinel twin, in this case here, now I'm simulating a mirror plane. And when I overlap those, you see we don't have yellow and red anymore. We get orange.
Yes.
So we get like a mixture of the intensities.
Okay.
So you see the diffraction pattern, the positions are the same, but the intensities are wrong.
Okay.
And typically that makes it very difficult to solve and refine the structure. Mm-hmm. So these twins are called merohedral twins because all the spots overlap.
Okay.
Then if we go to lower symmetry, in this case something monoclinic, you see we have an angle that's not 90 degrees. I did a rotation by 180 degrees. When we overlap them, you see we have sort of a mess.
Yeah. I mean, certainly, especially if you didn't have the lines there, it would really.
Exactly, and unfortunately, when you look at diffraction patterns, the software is not good enough to overlay lines right away. Yep. That's basically what you get from indexing. But you can see here, this is where the lattice planes are shared in the crystal, so they overlap. And then you see we have pairs, closer pairs, and then they get really close. And that makes it difficult to determine a structure. So basically, twinning is problematic because with these interpenetrating diffraction patterns, it's difficult to determine the unit cell. You can imagine if you look for the smallest unit cell, which the green one is the right one, when we index, we'll actually find something that looks more like this.
Yeah.
And this will be able, when you repeat this over and over, this will be able to describe most of the spots. So it will be happy with that. But it's not the correct unit cell. And then also, we use systematic absences. Translational symmetry gives you systematic absences, so reflections will be missing. We'll use that to determine the space group, to determine the symmetry of a system. Those will be obstructed, and then we already talked about mixing intensities.
Yep.
That makes it all difficult.
Okay.
And what we will do now is, in a little software demonstration, we will just deal with the first part, the unit cell determination.
All right.
Yeah.
All right. So, so the software now that can really elegantly handle these issues, right?
Yes.
Okay.
Yep. And we'll look at this in a second.
All right.
Okay. So this is APEX4, and it's already started up. And what I display here, that's methylpiperazine. It's a nice little small molecule. And fortunately or unfortunately, most of those crystals are twinned.
Okay.
And they're twinned, again, in a symmetrical way. Often people, including myself, when we have bad quality crystals and they're just split, we will call them twin. But technically, they're not twins because it might be just a 5-degree rotation.
Okay.
So it's just an imperfect twin, or imperfect crystal. So let's look at some diffraction patterns here. So these are diffraction patterns, and in the single crystal world, we don't get the birings, we get individual spots.
Okay.
And I can just play a little movie, gives you an idea how these reflections look like.
Kind of looks like a starry night.
Yeah, it does. And so at first glance, when you look at this, you might not even see that it's twinned, but then you get a little indication right on the first diffraction frame. There is one where you have very close distance. That would allude to a large unit cell. In other images, we see pairs of reflections. There again are these pairs of reflections. We see an overall structure, but then here they get very close. And here's a good motif, where you have these holes. These things typically are first indication that something is not quite right.
Okay.
What we will do is, this is a 180-degree. I will actually delete the reflections that I already had collected or harvested. We'll do this again. I will now harvest reflections, which means I will read all the reflections or the spots from the frames. We'll put them together, and then we'll put them in reciprocal space.
Okay.
Where all these reflections sort of live. And when we look at this in the reciprocal space viewer, right here, we already see that something is not quite right. So when you look at this pattern,
yes,
and in a single crystal, you would expect a pattern that shows rows of reflections and lattice planes, and right here, that's a really good sign for twinning the zigzag, and you get an idea that you have two lattices in reciprocal space that penetrate each other. Do you see the zigzag?
Yes, yeah. So it's like a little lightning bolt. Almost,
and you see this here, and typically you would only get nice lines. Here in this direction, everything looks fine.
Yeah.
And then we have other directions where we see these funny patterns, and if you remember that second example in my PowerPoint presentation, that looked almost similar.
Yes.
Where we have reflections at the zero layer here that all overlap, and then we have two arrays that just are oriented in different directions.
Yes. Yeah.
In this case, it's a non-merihedral twin, so they do not completely overlap. But this is a special case here, because you see that actually in every 1, 2, 3, in every fourth row, the reflections overlap completely.
Yeah, they come back together.
Yeah.
Okay.
And this is called a reticular twin. So here you have a mixture of non-overlaps and complete overlaps. And now what we have to do is we have to find the right unit cell.
Yeah.
And typically it's about deconvoluting the diffraction pattern.
All right.
Okay, we have some tools here. You see, we were able to rotate this already. Now we'll show you like two different methods to work with this. So what I will do is I will use a box selection in this case, and let me try to orient this a little better. And we'll use a box selection. And as we said, we know that in the middle here, everything overlaps.
Yeah, they're well aligned.
Yeah, so that certainly belongs to one domain. I will clear the selection again. And if you could turn off the live feed, then we see maybe the tools a little better. So we put these, we select these, and then we know, because we have pairs here, every second reflection belongs to a domain. This method is maybe a little more useful when you really know how twinning works, but then it's really powerful. So here I select them on top, and you see get these lines, I basically select these on the bottom, and then you see how it moves in this direction. So we need to select only a few of these reflections, and then that will be enough to index.
Okay, so you just have to give it enough to get started,
Exactly.
and then it can go from there.
So what I will do is, we have this nice feature that we can put reflections into different bins, and they're color-coded, so we can keep them apart. I want to keep the ones that are selected now as my first choice. So what I will do is I will invert the selection, and then I will put all the other reflection into the second group here, into the green group.
Now, is that going to be a problem that you didn't select all of the reflections for that one?
No, in this case, we only need to determine the unit cell. I will not delete the reflections from the diffraction images. So when I turn this off now, the green one, you see I rotate this, you see we now have a pattern that looks much more like a single crystal pattern. So what you can also see here is I selected a couple of reflections that shouldn't be there. I will just use the box again, and then we'll put those also into the green box. When I go back to indexing, you see now that we have two bins, the gray reflections and the green reflections. So what we will do is now we will index, and we say index the green reflections into my green container for a matrix. A matrix describes the relationship between the crystal system and the goniometer system, and it includes the unit cell information. So we index this, and we have a pretty good fit. Wow,
that was pretty quick.
Yeah, we have two different methods that give us the same information. So we accept that. We'll refine this. Talk about this later a little bit. We can also do a Bravais check, and it wants to be monoclinic, so it's a little bit of symmetry. Now, when we go back here, and then you see this is the unit cell that it has found, and it finds the right unit cell just because I filtered these out. When we press F1, we look along A star. F2, we look along B star, and F3, we look along C star.
Okay, and I could see there how it was lining up with that one set of reflection lines, like you had said.
So now that was just to show how we indexed the first domain. What we can do now is we can use this domain functionality, because we know we have at least a second domain. And per definition, a twin, the unit cells need to be the same. Their orientation is just different. So what I will tell the software now is use this unit cell or matrix, and now look in the green reflections and find more domains.
And then the green reflections were all of the reflections that were not included with the
exactly that were left over.
Yeah.
And so it found one additional domain, and make this move this to the side. And you see that here you see that the twin law. So they're related by 180 degrees rotation, and then there's also a rotation vector. In this case, it's a reciprocal vector. 0, 0, 1.
Okay.
So around this reciprocal vector, so around reciprocal C star, or C star is reciprocal, that's where we have our 180-degree rotation.
And yeah, and I think we kind of saw that in the data. How it did line up along some direction.
So when we go back here, so I will accept that, just to double check. And the reciprocal space viewer is nice because you can do sort of a sanity check.
Yeah, yeah.
So when we look at, we have these two unit cells now. I can zoom in a little. And again, if we look at along A star, B star, now we see the relation to each other.
Yep.
You see how these two are related. We can display these by domains. That's interesting. I thought I turned that off. So we will display this by domain. And now the software will just highlight them in the domain with the green cell and the gray cell.
Okay.
And now you can see, this is C star.
Yes.
If we rotate by 180 degrees, do you see how this green reflection will actually turn into this gray reflection here? This is how the two domains are related to each other. And that's the twin law, the 180-degree rotation around C star. So ignore that. So this is one method how we can index. We're running out of time a little. There's other methods, also more automated methods. I will just show one where we can do this. There is a method here, a least squares method.
Okay.
And what we can do here is we can do a specific unit cell search. Typically, we search between maybe 3 angstroms and 45 if you use this method.
Yeah, yeah.
But we had seen that there is not a really long unit cell axis in this case. So if we just reduce this to maybe 12, and we can measure in reciprocal space, we can measure distances and use this for indexing. And we turn off maybe the first two, then this might actually also fall out automatically.
Okay, so you just basically put some boundaries on it, and then it can do it automatically.
So this was basically a black box indexing. It's a little boring to show because it just works.
It works, and sometimes that's good, as long as you have the right assumption, right?
Yep.
With those boundaries.
And this is why I always tell people to look at reciprocal space. Because humans are very good in picking up patterns. Yeah. We had seen the zigzag patterns. You could have also used the zigzag patterns and a plane overlay tool to select those and then get your first domain and then get your second domain. And here we would do the same thing. We found one domain automatically now, and then we would do the same thing. Again, we say in the yellow, use the yellow unit cell, and again search in the green reflection bin, search for another domain, and it should do the same thing.
There we go.
So this is basically just the first step to being able to determine the unit cell. Yeah. Then there is, of course, more steps, and maybe we could talk later if you invite me again. Yeah, definitely.
Another
about
episode
how
of Live
you would
from the
then
Lab.
Determine the intensities. Yep. And also deconvolute the intensities when you have overlaps. And you need that to be able to solve and refine the structure.
Okay. And so one question I had about APEX4 now, that is the software you use for everything, right? So
yes.
Starting the measurements, doing the measurements, results, everything.
It's a complete software suite. You see this plugin structure. We use different apps or plugins in the structure with the framework. Okay. And there's like 40 programs in that suite or plugins that you can use to determine a structure or tackle more difficult problems.
All right, but you've put it all together in a way that it's the right tool at the right time
exactly.
for the processes. So now that we've gone through that demonstration, we are ready to answer some questions. So if you have any questions, go ahead. You can type them in YouTube there on the right side, and we will get to them right now. Otherwise, if you have a question later, you can always send it to our email address. And that email address is live.events@bruker.com. Now, we do have a few questions that did come in before the broadcast. And the very first one is from Karen, and that question is APEX4 available for download?
APEX4 is available for download. If you're familiar with how Bruker set up, we have this website, brukersupport.com. So if you're a customer, you can download APEX4 from there. And that's also where you get updates, updates for free. You can also request a temporary license. So what I might want to do is I can put together a package for this presentation. If you contact us, then we can give you a temporary license and provide you with the files.
Okay. Yep. So, so you mentioned a license. Now, is this one of those softwares where you kind of every year you have to pay for the license, or is it that like you buy the license once and then it's good for?
Yeah, you buy the license once. Typically, you get it with the instrument. So if the first version of APEX was released, I think, in 2001. If you have that original license, APEX4 will work with that license.
Okay. Yeah. Okay. So next question is one that actually came in here, and that is from Yasin. Is twinning like this always visible with an optical microscope with a polarizer?
That's a very good question. Because we look not very often at large minerals, so there is extinction of light with crystals that is visible with a polarized microscope. So if you have a certain system and you look at the crystal under polarized light, then light will be extinguished. So when you rotate your crystal, you see it's going transparent, light, dark. You can see that. Unfortunately, with higher symmetry, that goes away. And it certainly helps if you have cracked crystals, the quality. But for example, this piperazine crystal, that looked perfectly fine under the microscope. But polarizing microscope is certainly a good idea for crystallography, and it can help you to see twin crystals. Some of these swallowtail twins, you would see the shape, but they would also extinct light differently. The two parts, domains.
So next question would be from Zhao, and that is, can I get a temporary license? So you've already answered that one. Yes, we can provide a temporary license for that. Next question is from Kevin. What is the best way to solve merohedral twins?
Merohedral twins are tricky because at first glance they don't look like twins because we have that complete overlap, so they're easy to index, and then typically you're stuck. They're also high symmetry. By definition, they have to be high symmetry, which you have lots of choices for space groups, which doesn't make it easy. So you're typically stuck at when you try to determine the structure because of the overlapping intensities. There is software that can try to deconvolute if you can sort of make a guess how much how big the domains are relative to each other. And there's also one software where you can use the twin law to try to solve the structure. That would be the dual space method. In APEX. There you can specify a twin law. And because if you have a merohedral twin, there's maybe just a handful or more twin laws. I typically just try them all, and then I hope that...
See which one works best, huh? So, I mean, it's always good to bring that sort of experimenter back into it, right? You have that knowledge going into it. All right, next question is from... let's see. We've got quite a few questions coming in, so keep them coming. And this is from Pani, and that is, can you suggest what to do when the structure solution fails? It's kind of a big question, huh?
Yeah. Especially with twinning, and depending on how good your data quality is.
Yeah.
You know, the single crystals, everything is so well tuned, it's straightforward.
Yeah.
With twinning, you often have to go back several times, reprocess your data, trying to get a better understanding, trying to get better reliability criteria for your data. And then it's often working even with the international tables,
Yeah.
and to look for subclasses of space groups, because you might get fooled into, you know, higher symmetry. It's a lot of trial and error, I would say.
Yeah.
With twinning, often they don't always pop up out as nicely as the methyl piperazine, for example.
So, can you actually have multiple twins present?
Yep.
Or do you generally only have one because of the kinetics and stuff?
So you mean, yeah, there are systems where you have, sometimes with phase transitions, and let's say you have a hexagonal system and then a phase transition goes to a lower symmetry, then you might have a six-fold twin. I've seen those.
Okay.
Four-fold twins, just depends. Yeah.
All right. Next question is from Suvik. Can we solve the twinning from the twinning option given in APEX4 by creating a virtual cell?
So, virtual cell, basically you have to determine all cells or all matrices that describe the individual domains.
Yep.
Then you can do an integration during scaling and absorption correction. You deconvolute and you write out a file that you can use to solve the structure. And later, there's a special HKL format, HKLF5 format, that gives you information about domains and how they overlap. That is later used for a twin refinement, for an HKLF5 refinement. So yes, you have to be able to describe all domains to be able to integrate them at the same time, deconvolute them for structure solution, and then you use sort of the convoluted file to do a twin refinement.
All right. Let's see here. Next question is from Kuldeep. Hello, Michael Roof.
Hello.
Well, he's out there. How are you? Nice to see you again. I am getting total 4 domain, including main domain, with angle like minus 17 degrees, 0.4 degrees. Is twinning or something else?
So in this case, it's per definition, it's not a twin. It's like a split crystal, or it's just like a bad quality crystal. There's sometimes nothing you can do. That's the way they crystallize the clump. The good news is that although it's technically not a twin, the tools are the same that you would use to process these split crystals, these clumps. Because you see in the example, in the PowerPoint example, with the monoclinic plane, you have the same problem. You have reflections that get really close. They overlap. They partially overlap. The software handles that. The software really doesn't really know anything about symmetry in this case. So yes, you can use the same methods. It gets trickier the more domains you have. You can also imagine you have a crystal that's 100 micrometers. Let's say it's isometric. If you have 4 domains, they're all only 25 micrometers. So each of them is actually much smaller than you would anticipate, and you only get a quarter of the diffraction. Another problem is if you have these kind of twins, they might be that one domain is really strong, and then all the others are very weak. So let's say you have the strongest domain is 80%. The next one is 10, and then 5 and 5, if my math is correct. So that means you have one domain you can determine probably pretty well. The second one maybe. The other domains, they're just annoying because they will falsify your intensities because of the overlap. But those twins are then, or split crystals, are pretty difficult to handle.
Okay. So next question from Amit. What is metric merohedral and sigonic merohedral twin?
I don't know.
Killed those names, so it was, let's see here, metric versus sigonic.
I have not heard that, to be honest. So I won't even try to wing that.
Stump the expert. Yeah, that's what we did.
I won't.
Okay, from Suntandayu, is checking twinning only through reciprocal lattice? So, we use that reciprocal lattice tool to kind of look and see if we saw something.
Yeah, I like to do this, and it's a very powerful tool, and I use that for quality control. Mm-hmm. So I will mount a crystal. We collect this fast scan. It's like a 3-minute scan. The data we looked at. You load this into RLAT, a very quick look, and you see, okay, something's wrong. If I have a lot of other crystals, I will go back and look for more.
Yeah.
It's very fast. Microscope helps. There are other signs for twinning that you can see later.
Yeah.
For example, what we use a statistic which uses normalized structure factors. It's called the E-value statistics. What it basically does, it looks at the distribution of your intensity in your data set. That's useful because centrosymmetric structures, the difference in intensity is larger than with non-centrosymmetric structures. That can help you to see, is this P21 or P21 over M, for example.
Yeah.
And you get the idea, if you have an overlap, you will wash out the intensity, they will look more even. So if you have a very low E-value statistic, that's a really good giveaway, especially for merohedral twins, that this might be twin because it's so low.
All right. Yep. So check the E-value and the reciprocal lattice.
Exactly.
And you should cover all the bases there. All right. From Eric, are specific tools better for different types of twinning?
Use them all if you can. Yeah. I'm a very visual person, so for me, finding these patterns, seeing these patterns, and I've done it for quite some time, is very easy. Mm-hmm. And it's also because I demonstrate software a lot. If you click on a black box system and it just pops out, there's not much to talk about unless you want to get deep into the algorithms. And I like RLAT because it's hands-on. You can actually do something, virtually do something with the data. Use all the tools you have, and use whatever you feel most comfortable with. That's
and getting experience with it, right? That's that part of being a good crystallographer. All right, from Sidodine, how APEX4 can help to solve structure of twin crystals that also present disorders.
Okay, so these are, of course, really two different things. So twinning, you have interpenetrating lattices. Yep. Disorder, what that typically does to your data set, it will introduce amorphous scatter, and it will also limit the resolution. So especially with organic molecules that are disordered, you get often good diffraction to maybe 50 degrees, that's 0.9 angstroms, and then it just falls off radically. So these are really two different things. Of course, if you have a twin and the structure itself is disordered, nothing would really change in how you handle this. You might have to be careful in having, longer exposure times maybe to push that fall off a little bit further out to get the resolution you need for a good structure determination.
Okay. So from Ping Rong, can we use CellNow to determine two domains? Yes.
And what you have actually seen there in the APEX software, this part, the least squares indexing, this is actually CellNow. So we use CellNow as one of the engines. And then that's for finding the unit cell. And if you're familiar with CellNow, that's a command line based program, a Bruker program. And the second part will actually look for more domains. The domains functionality in APEX, that actually uses also that part of CellNow. So if you use APEX4, you will use CellNow. If you want to use the command line version,
Yep.
that's fine too.
Okay.
And they will work just the same.
All right. So APEX4 though gives you a really nice GUI for working with it. All right. From Manu, is it okay to omit non-merohedral twins if it is less than 5%?
The beauty is that if you have a merohedral twin and it's only 5%, you could ignore it, but, and this is what a lot of people actually suggest, if you have a system that can show merohedral twinning, to always try the twin laws, because this is really just a line in the instruction file for the refinement. And those few twin laws are readily available. If you look for them online, just try them, and your R value, your reliability factors might drop, even if it's just a 5% twin.
5% is 5%, right?
5% is 5%, but it might really drop quite a bit.
Okay.
So always try.
And then one last question from Manu. Is there a relation between non-merohedral twins and whole molecule disorder?
A lot of people know how I feel about whole molecule disorder. In a lot of cases where there was apparent whole molecule disorder, it actually turns out to be something else. In a lot of cases, I have seen that there's a modulation that's not described. So there's something else wrong with the data. And sometimes it's not easy to see in the data.
Yeah.
And you're describing the system as a whole molecule disorder is the next best thing you can do.
Yeah.
I don't really believe that is there's something else wrong with the data. But per se, I wouldn't say that there is a direct relationship between twinning and whole molecule disorder. I think it's between modulation that's not recognized and whole molecule disorder. That's my personal opinion, and I probably poked the hornet's nest by saying this in this
So whole
episode.
molecule disorder sounds like that's kind of this big bin where you could put a lot of excuses into, but
I mean,
that's not
when
the
you
right.
refine the structure, it really looks like there's whole molecule disorder. Basically, what you see is like you have your molecule, and then there's like a little shadow of the molecule to the side, and the main molecule might be 80% or 90%, and then there's a little part of a shadow, and
close, but not quite right.
Exactly.
All right. What the heck? We got one more in. This will be the last question, though. So this is from Kuldeep again. With HKL F4 getting nice I over sigma, but with HKL F5 getting I over sigma around -1, what does this mean?
That means that probably something during the processing did not go quite right. So in an ideal world, refining against the HKL5 format file should give you the better result. But I have seen cases where the HKL4, where the software actually deconvolutes the data beforehand, works a little better. But send me a DM, I guess.
There you go.
And we can talk about that. I can also look at your data. But that should not be the case.
All right. And speaking of that, if you do have any other questions that we weren't able to get to today, you can go ahead and send them to our email address. That email is live.events@bruker.com. So thank you for joining us today, Michael.
Thanks, John. That was a lot of fun.
Yeah, we'll definitely have to have you back on so we can go more into depth into those more advanced analyses.
Sounds good.
All right. Until next time, everybody keep your signal high and your background low.